So maybe we can start. So I'm really happy we have Romain today for his talk on the cyber resilience of complex systems. And I'll let Romain introduce himself. So the floor is yours.
Thank you, Francesca. So hello, everyone. My name is Romain Dagnas. Thank you very much for attending this presentation. I'm a PhD student at Télécom Sud Paris Samovar and a research engineer at SystemX, IRT SystemX at the CEA. And I'm going to present to you the subject of my research topic, which is the cyber resilience of complex systems. So this works and these contributions has been realized in collaboration with Michel Barbeau from Carleton University at Ottawa, Canada, Joaquin Garcia Alfaro from Télécom Sud Paris, and Reda Yaish from SystemX. So today we're going to talk about mainly cybersecurity and cyber resilience from a quantitative point of view. Okay, I'm going to follow this plan for this presentation. First of all, I will introduce some context elements related to cybersecurity and to the protection of critical infrastructures in general. Then we will define what is exactly cyber resilience, because I know that maybe a part of you is not familiar with this research topic. So we will define it and see how we can use this research axis for cybersecurity purposes. Then I will present the main contribution of this presentation, which is dedicated to a quantitative resilience analysis of an example of critical system that we considered here, and it is the SWaT. And then we will discuss about the results and finally conclude this work. If you have any questions, feel free to interrupt me, to raise your hand, so I will answer. So first of all, some context elements. We know nowadays that with the race for digitization and the increase in competitiveness, that critical infrastructures become more and more connected and thus more and more exposed to cyber attacks, cyber threats, and cyber adversary. And there is a real need to protect these critical systems. So as examples of critical systems, we have nuclear plant, water distribution, electrical distribution systems, and so on. And these systems are called critical because they must answer the completion of very sensitive missions. Sensitive for people, for states, for countries. We see the impact that an attack on a nuclear plant could have. So there is a real need to protect these critical systems. And one solution to protect these systems is to use the resilience, to improve the resilience potential of a system. But we will define it later. As example of attacks on the context elements, there was a lot of cyber attacks during the last years perpetrated against critical infrastructures. For example, in 2021, there was the attack of a water treatment station in Florida, during which the adversary attempted to give an amount of sodium hydroxide that was 100 times higher than the normal amount, which is a bit spicy, if I can say, for human health. But here, once again, we see the impact on human lives. So there is a real need to protect this. There was also the attack of a colonial oil pipeline, and more recently, the case of Killnet, which perpetrated DDoS attacks at Ukrainian allies. And also more recently, Logbite, which perpetrated cyber attacks against French infrastructures, hospital, banking, etc. So now we will introduce the notion of resilience with some notions from the literature. There is various definitions across fields from the literature. The first definition that we know came with Holling in the 70s from the field of ecology, where the resilience was defined as the capacity of a system to move from a stability domain into another one. Then this notion of resilience raised other topics such as psychology, sociology, computer sciences, engineering, and more recently, cybersecurity. And this definition is very interesting. So in the context of cyber physical systems, because here we talk about critical infrastructures and complex systems, this is a big family, the family of cyber physical systems, because these systems integrate hardware and software components that communicate with the cyber and the real world. So they are called cyber physical. And for cybersecurity purposes, we call the resilience as the system's ability to recover or regenerate its performance after an unexpected impact produce a degradation of its performances. And here what you can see is a traditional, if I can say, graph of resilience. Here we have the performance of an abstracted systems, and here we have the phases of resilience, namely anticipate, withstand, recover, and adapt. And in the resilience postulate, we consider that the zero risk does not exist and that every kind of systems can be attacked. So based on this, how can we protect a system? How can we apply countermeasures and resilience measures that make him stronger facing cyber attacks? So in the resilience postulate, when a disruption occurs, we assume that the system will lose a part of its performances before reaching and bouncing back to a stable state. Okay, and we want a system to have the enough potential to do that. Here you have three different scenarios. We have the red scenarios during which the system is facing a disruption. It can be a natural event like the Fukushima case, but it can be also a cyber attack. And the red scenario illustrates the fact that the system is not able to recover its performances. It works in degraded performance. We want to be in the blue or ideally in the green scenario where the system is sufficiently resilient to learn from the attack in order to have a gain in performances. This can be done by the bias of specific countermeasures, which means that if we play the same attack twice on an infrastructure, the attack will not have the same impact because the system is able to learn from this attack and to deploy specific countermeasures. As it has been highlighted by Kot and Linkoff, to be able to improve the cyber resilience of a system, we must be able to measure it. Measuring cyber resilience implies to use metrics that could be qualitative or quantitative. These metrics are based on properties of the system. We call also KPI, key performance indicators. And for example, on this graph, we have the quantification of the performances here. So a metric quantifying the resilience can focus on the performance of the system in order to quantify if it is sufficiently resilient in the case of an attack. So the first challenge is to build these metrics. The second challenge is to build accurate systems. Nuclear plants, water treatment systems, and these systems are by definition difficult to model. So how can we find the good level of abstraction in order to be apply these metrics and to have a good estimation of the resilience? And two important pillars of resilience that we must consider are the observability and the controllability. You can consider that if your system is observable and controllable, it is resilient. Why? Because we need observability to be able to detect an adversarial event, to detect an attack. This can be done by the bias of sensors, for example. And we also need controllability that can be improved by the bias of actuators. And this is important to bounce back from a stability domain to another one. When the attack occurs, if you remind the graph that we have, we bounce back to a stable state. This is done by the bias of controllability. So you have here the two pillars of resilience that it is important to consider. Now I will present the approach that we published in previous publications in the literature. We propose to use knowledge graph to model these critical systems. And why? Because with knowledge graph, we have the possibility to model various entities. It could be components, function of the systems, or abstract entities. And we can also model a various diversity of relationships between these entities. So we use knowledge graph according to a multi-layer model that I will present later. And the idea is to map components of a critical infrastructure according to the role they play. We have, for instance, a physical layer with all the physical components. We have a sensor layer with all the sensors of the system, a layer for actuators. And the idea is to consider the fact that we can apply a resilience assessment to each one of these layers in order to know that if there is no layer with too much resilience at the detrimental of the other ones, okay? To have a global idea of what is the resilience of a system. And we use graph analytic metrics to quantify this resilience. So here is the description of this methodology, multi-layer modeling, as I said, using knowledge graph for various entities and links relationships modeling. And for the graph analytics part, we used the eigenvector centrality metric. So you don't have to focus on the mathematical definition of eigenvector centrality. What is important to know here is that on a graph, the eigenvector centrality quantifies the importance of a node according to the importance of its neighbors in the graph, okay? So by this bias, we can quantify the resilience. And the interpretation that we make about this metric and its numerical value, it's that if we have two architectures and we quantify the resilience, if we have a low eigenvector centrality on an architecture, it means that we have a gain in resilience. And why? Because it means that the relative importance of each node in the graph is lower than in the first architecture. So if an adversary tries to attack one component, for example, in order to generate cascading effects, it will not have damaging consequences because each node is low critical than in the previous architecture. Okay. Yeah.
Yes. So I understand at least qualitatively that it will give an idea of the importance of how resilient is an architecture. But is it also quantitatively? Will you show some results on this? Yeah.
Yes, I will show some results. The eigenvector centrality is quantitative. It's not qualitative, yes. The two architectures that I talked about was just to make a comparison of the interpretation of the metric. But the results are quantitative.
Okay.
So here you have an example of what is the multi-layer model that we consider. The first three layers here are the same. As I said, we consider a physical layer. We use components in this layer that do not play a role in the resilience enhancement. Here we have the observability potential with the sensor layer, mapping all the sensors in an architecture. Here we have the controllability potential, including controllers, for example, pumps and valves, etc., etc. These layers are used to quantify the resilience. And then we have transversal layers that cover the whole graph representing an architecture. For example, the cyber layer mimics what an adversary could see if he spies the network in order to find a component to attack on the system. The adversary will not be able to find which components plays a crucial role, but he will be able to analyze the data exchange between these components. For example, he can see that there is sensor readings sent from a pump to a controller. And with this knowledge, an adversary can build its own model of an architecture. Okay? Yes.
Another question. So when I look at the figure, I see that there is an arrow from actuator to sensor, which seems strange for me, but there is no actuator to physical. So you do not act on the physical infrastructure in that case.
But for example, there is a sensor attached to an actuator. For example, you have a pump that we could have a sensor.
But the pump is on the physical layer.
The pump is on the actuator layer.
Ah, okay. Well,
in the physical layer, for example, we have, if I can say, components that are not actuator or sensors. For example, a tank. A tank is not an actuator, it's not a sensor, okay?
Okay.
And these components, so here, for example, here in these three layers, we have a whole graph. And here, the two top ones, we have transversal layer that cover the whole graph.
So actuator and sensors are physical objects that you detach from the physical layer in that case.
We detach it from the physical layer, yeah, absolutely. Maybe we can rename this one, the physical one, but... And the mission layer is, if I can say, a logical layer, including what each component is expected to do in order to complete a mission. For example, a controller must act on a pump. A pump must send its sensor status to the controller. Each step that must be followed is present in the mission layer to be sure that the mission will be completed. Sorry. So now this was the theory part, and we will go through a resilience assessment of a specific kind of critical infrastructure, which is the SWaT. I don't know if you are familiar with the SWaT. It is a secure water treatment system that has been built by the Singapore University of Technology and Design. So this testbed that you can see here mimics the real behavior of a water station in Singapore. Okay, so we have the real components, we have the real processes, everything looks like the real system. Here you have the 6 substages of SWaT, namely pumping, chemical dosing in order to purify the water, ultrafiltration in order to remove the biggest particles from the water, dechlorination with an ultraviolet treatment, reverse osmosis in order to remove bacteria and viruses, and the final stage. We will focus on the first stage of SWaT for this assessment, and the idea is to extend our approach to the overall system, but I will come back to it later. So this first substage of SWaT is presented here. Basically, what we have a tank, 2 redundant pumps in charge of pumping the water, send it through a pipe, then to the stage 2, that is not modeled here. And we have a controller in charge of acting on the system. And we have here lectures of sensors sent to the controller and control actions sent to the pump. We know that to be resilient, the system must be observable and controllable. So we will play with these degrees of observability and controllability. What happens if we add more observability? Do you have any ideas on what we can add to increase the observability? More sensors, yes. But if I can say not redundant sensors, diversified sensors, because it has been proved that if we had redundant sensors, from the point of view of an adversary, attacking one or both is the same thing, okay? So if one sensor can be attacked, both can be attacked. So which one can you trust? If we have diversified sensors that measure different physical phenomena, for water treatment purposes, it can be flow rate, it can be turbidity for the water, it can be pH. All these things, we can map it to the water dynamics. From one measurement, we are able to discover if there is one sensor that do not tell the truth, if there is one sensor attacked. So this diversity is very important for resilience. And if we add more controllability to the system, we can add, for example, a redundant controller that plays a role in acting on auxiliary pumps. For example, if one of these 2 pumps or both are attacked, the controller is able to shut down these 2 ones and to start this one in order to act on the 2 auxiliary pumps. So the system is able to bounce back to a stable stage if one of the pumps is attacked, for example. Yes?
But, using your reasoning as before, if you can attack the first 2 pumps, the attacker can attack in the same way the other 2 pumps, right?
It is possible. Here it's not represented, but we use pumps that has not the same technical specifications, you see. For example, pumps that have a rotation speed here. For here, we can have only start and off pumps. That so for the adversary, it's not the same components to attack, but it is a good question. Yeah, thank you. So now that we have these 3 architectures, we are going to model it by the bias of knowledge graphs, as I presented it earlier. So for the first architecture, we have this graph, which is a kind of simple. But if we had more observability and then more controllability and observability, we see that the graph gets more complex with more links because we add more components. Once we have these graphs, we are able to apply the eigenvector centrality that I presented earlier in order to quantify the resilience. Oops, sorry. As a reminder, for the eigenvector centrality, the interpretation that we make is that if the value decreases across the architectures, we have a gain in resilience. So we want a value close to 0, ideally. So basically, if we think about a graphical representation, and if we think that here we have our three architectures, namely A0, A1, A2, we want the eigenvector centrality to be as close as possible to 0, okay? Here are the results. The figure looks complicated, but they are not, okay? Here you have the 5 layers of the model, namely physical, sensor, actuator, cyber, and mission. We quantify a mean eigenvector centrality represented by the blue squares for each architectures, A0, A1, and A2. And if we look at each layer, we see that from A0 to A2, the eigenvector centrality decreases. So according to this metric, there is a gain in resilience. You can see all the details on these figures, the yellow area and the red points. These red points are points called as critical, the most vulnerable points that plays a crucial role in each architecture. These critical points, if attacked, can generate cascading effects with damaging consequences. And why? Because according to the eigenvector centrality, they played an important role in the system's behavior, okay? And according to our approach, if these red critical points are located in the yellow area, they are considered as protected. According to this approach, we stipulate that the yellow area mimics or reproduce a kind of resilience noise in which an adversary spying the system is not able to make the distinction between a critical point from another one, okay, due to the density of links. Yes?
So according to the first picture that you showed, the eigenvector, the previous one, the eigenvector centrality should go, you say, close to 0, right? But in these figures that you mentioned, the eigenvector centrality assume also negative values. And is there an immediate understanding for why? So what would it mean?
Basically, it is a relative value. So there is no, if I can say, a real interpretation of if the eigenvector centrality is negative, for example. But it is, let me look at this. We actually do not have an eigenvector centrality negative. We just have a standard deviation that is negative here. The yellow area, here we have a mean.
Okay.
Here we have the standard deviation. And for each layers, we have positive values. This is just the window of the graph that is extended to include the overall yellow area, if I can say.
But the area, what does it represent?
It represents this resilience noise, you know. It means that, how can I say that? The eigenvector centrality works with the density of links in a graph, with the importance of each node. And we assume that if critical points have an eigenvector centrality that is comprised in the standard deviation, from the point of view of an adversary, it is not possible to find accurately these critical points, because there is a density of links that is, if I can say, common to on the all components. But here, for example, an adversary will be able to identify it if he spies the network traffic, for example, the transmission of data, or yes.
So this is even once you have the graph.
Absolutely.
So I mean, what you're showing is basically the spectrum between a fully centralized system and a fully distributed system. The more distributed you are, the less you need to rely on a single node
yes.
not failing.
Yes, absolutely. But we have to be careful with this kind of modeling, because our more recent results show that even if we can protect these critical points by complexifying an architecture, bringing more steerability, controllability, observability, we can also create new critical points on these architectures. So there is a thin balance to find between having a resilient system and protecting these points. For example, if it is more important to have one single critical point, we will try to protect the other ones. There is existing systems that have, for example, 6 critical points, but they are protected. So is it better than one critical point that is not protected? This is the question. Yes, Ludovic?
So then I have some questions about the red points.
Yes.
For cyber layer and mission layer, they are not protected, if I understand your
Yes.
for all the architecture. And it is even worse with sensor layer because they are protected with the simplest, the first architecture.
Yes.
And the last one that we supposed to be more protective, it's not the case.
Yes. Yes.
But it's not the case, but the position of the point goes towards zero.
Yes.
So is it a good indicator?
It can be a good indicator if we consider that the system has enough potential to absorb an attack. If the critical points are exposed, but the system is able to react, okay, it's fine. But once again, we have to be careful with this. We try to make these critical points as close as possible to the yellow area in order to protect them. Is there other questions?
Yeah. Again, a question on the red points.
Yes.
So, and the definition of a critical point. So, do you define a critical node or point or whatever it is, like because of your knowledge of the system, and you know that thing is a critical point, and then you show it on the graph, or you define a critical point? What happens to be a red point there?
If I understand well your question, these critical points are identified once we have built the graph and once we have applied the metric to quantify the resilience.
Okay.
These critical points are basically the components with the highest eigenvector centrality, because it means that there is a high degree of connectivity with the other components, you know? And what we call critical is that we think about an adversary trying to generate cascading effects. So if an adversary is able to attack one of these points, we know that as it has a high degree of connectivity, it will generate a massive cascading effect in the overall systems across the overall layers.
Okay, it's clear. The standard deviation is standard deviation of what? On this measure of eigenvector centrality on all the nodes?
Yes, yes. Basically here we have the physical layer. We have the physical components in it. The blue square is a mean eigenvector centrality for all the physical components in this layer. And if we have a mean, we are able to have the standard deviation. So we have modeled it for each layer because we apply a mean value to all the components across the layers.
The red point is the one with the maximum eigenvector.
Yes. Yes.
So if it's okay, so the maximum is within the standard deviation range. This is what, right? But anyways.
Basically, it means that if with a high eigenvector centrality, we are in the safe area of the standard deviation, it means that maybe all the components have approximately the same eigenvector centrality. Approximately. So it means that the challenge is very difficult for an adversary to find which point is critical in comparison to another one, because they have approximately the same degree of connectivity.
The concept I understood very well. The fact is that it's difficult for me to imagine a distribution of values in which mean plus standard deviation is larger than the maximum, but maybe it's the case.
Sometimes it's the same. I was also surprised by these results, but basically it's the same for this layer.
Here.
So in order to compare these results with other metrics that we have previously introduced, we will conduct other resilience assessments in order to see if the eigenvector centrality tells approximately what looks like the truth about resilience. But each metric will not tell the truth. Okay, we only have an interpretation and a view about what could be the resilience. So the other metric that I want to talk about is the KL resilience. It quantifies the observability and the controllability of a system according to 2 degrees K and L. We have also another metric that we have used in previous work, which is a spectral radius. And this metric is interesting because we can also apply it to graph modeling. Graphs, or as you can see here, square adjacency matrices mimics a graph with a degree of links connectivity between two different components. So what happens if we consider these two metrics? Here we have the interpretation that we make. If the KL resilience increases with its two parameters, we have a gain in resilience. If the spectral radius increases, we have a gain in resilience. But if the eigenvector centrality decreases, we are resilient. So here you can see the results that we, yes. 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 So K and L basically are degrees. So I must say that this kind of modeling is only applied to differential equations. Okay. The K and L degree are used with correlation coefficient matrices. Okay. And basically the degree key, quantifying the controllability, is the number of actuators available to act on one only state variable. Think about a state space representation with matrices. It represents the number of actuators able to act on a Planck state variable. And it is similar for the L degree. It is the degree of sensors that are available to monitor one Planck state variable. But I agree that I didn't talk about this. We need differential equations and state space representations to use this metric. This is why it is hard to use it with complex systems, because building differential equations reproducing the behavior of the SWaT is very difficult. Or you will have maybe an equation that goes on 3 lines or more. So
Dynamics of systems method?
It is dynamics of systems, yeah, based on the control theory. If you are interested, I have a QR code with all the related publications, so you can find more details on it. So we will apply these two metrics on our architectures, namely KL resilience and spectral radius. And this is the results what we obtain. And we see that across the different architectures, we have a gain in resilience. One time again, according to what each matrix is able to tell, okay? So as I said, each metric will not tell the truth about resilience, but we have to choose what we want to consider and what reproduces the better, what we think about when we consider the resilience notion. Now we will discuss a bit about these results because we have to be careful with resilience enhancements. Indeed, we cannot increase the resilience of a system to an infinite stage. Okay, there is a limit, if I can say. And we have to find a thin balance between increasing the resilience and increasing the security risk. Basically, it has been proven that if we add more components to an architecture, it can also increase the attack surface for an adversary. We can have more critical points, and for an adversary, there is more possibilities to attack a system. So basically, the dark scenario here shows an equilibrium between the resilience increase and the increase in the security risk. The red scenario is a scenario where there is a high increase in the security risk. And we want to be in the blue scenario, the most desirable one, where the increase in the security risk is mitigated by the increase of the resilience potential of the system. Okay. So now I think the best is yet to come because we have modeled the secure water treatment system with all its 6 stages, as you can see here. This is the whole architecture of SWaT. And we are now applying our metrics to 3 architectures with different resilience potential, as I presented it earlier. So we have graphs getting more and more complex. I cannot show you the results today because we have not yet published the conference paper, but maybe in one next seminar, I can show you what we have found with these interesting results. So as you can see, it is a very complex graph that we have tried to model with our knowledge about SWaT, but it is a methodology that works if we consider the eigenvector centrality, which was not possible with the equation differential models that we considered with the KL resilience earlier. So to conclude this presentation, if I can say, as I said, we have to find the thin balance between the security risk and the resilience. There is also a cost associated to the resilience, because if we had more components, we have a cost to assume in buying more components, more sensors, more actuators. And there is a need to consider the environment in which the system evolves. For example, the human factor. Many of vulnerabilities comes with the human factor. So we have to consider the system in its environment. And the challenge here lies in building models that reproduce this environment with these complex interactions with the systems, with mission workflow, and so on. And there is also the challenge related to the protection of critical nodes. Because now, actually, with machine learning and all the IA-related methodologies, we know that adversaries are able to build their own model of a system based on information available online. So the question is, are they able to find the critical points and to attack them? And for us, are we able to protect them? So here you have the slide with all the QR codes related to our previous publications. You are free to take pictures and to go to read our papers. And if you have any questions, I will be happy to answer them. So thank you very much. Yes.
So do you need, like when you do an analysis of a complex system and you try to implement your model, do you need to start from scratch each time because it's different for each system, or can you use the same component?
Sorry, what do you say? Use the same scratch?
Like do your analysis to analyze your complex system and to build your model, do you need to start from zero?
Okay. We need to start from zero, yes, absolutely. And to find available informations, we have built the SWaT according to technical details available online, because it has been built by a laboratory, so data were public. But if we consider, for example, nuclear plants or maybe electrical distribution systems, we must consider an abstraction degree. But if we abstract some functions or components of the system, we will lose the accuracy of the metric. So this is why it is challenges in building these models. Other questions?
So I have another question about the fact that you have several layers, right? The physical, the sensors, the actuators, etc. So if you apply that same discussion that you had, so the fact that there are some parts that are more important, some parts that are more critical, etc., to the full stack of the architecture that you get, in my layman view, the physical world is confined within your domain, within your institution. So it's protected, let's say, by design. And so the more you go upwards to the hierarchy, the more you are vulnerable.
Yes.
So wouldn't it be, let's say, more effective to push most of the defense or the resilience mechanism towards the upper layers?
It is absolutely possible to put them on the upper layers. Here, we focused on resilience by design, in building new systems that are resilient and also making existing architectures being sufficiently resilient with new mechanisms. But as you said, it is also possible to consider a top-down approach. We put a lot of resilience measure at the top of the layers, and then we decrease. Because here we have to make a focus on a specific kind of attack. And I don't know if you know it, we consider what is called the covert attack. It is an attack that has been proven to be invisible, if I can say, because the adversary attacks the input signals of the controller and the output signals. So from the point of view of an observer, everything looks fine, but maybe the system is in an unstable stage. So we have to consider the system on the physical view to protect it and to deploy these adapted countermeasures. But as you said, it is also possible to consider the top view also.
And this is just a curiosity, but in the previous plot, the one where you were showing the security risk, because you said that you can also increment the surface attack.
This one?
Yes. So is there a way, how do you quantify the risk?
It is an abstract scenario, you know. We just have plotted some curve that describe different scenarios.
Okay.
So, but if you consider security risk, you can think about maybe risk is not a good word in this case. Maybe we can think about the attack surface, you know. Maybe the number of nodes that could be attacked in comparison to the overall nodes in the graph, for example. But we can also have a more accurate approach with a risk, estimating the probability of an attack, the impact it could generate. And for further research access, we consider the impact attack quantification problem in order to estimate this with numerical results.
So maybe it does not apply to what you are doing for cyber physical system, but in a purely distributed system approach, if you consider a multi-node scenario, each node has its own state machine, for instance, automata. And so basically one can just calculate the combinations of all the possible state of different nodes to find what are the one that will generate the most damage.
Yes. This is a good point because we try to consider KPIs in our new approaches, you know, and we know that there is KPI associated to each node in which there is a normal behavior to an abnormal behavior. So yeah, this is a very interesting research axis.
About this security risk, it reminds to me other things because I think your approach is really centered in the cyber view, really centered on the cyber question. But regarding resilience, I think you may know this paper by Sterben's 2010,
yes.
And there was a lot of recommendation on resilience. And some of them were, for example, complexity, control. This is like a resilience law that if your system is too complex, you may not be able to understand it and to control it properly. And there was also the principle of normal behavior knowledge. And I think these points are not only related to security, but also to the fact of controlling and understanding your system, because they are not only the cyber attack, there are also the failures.
Absolutely.
And regarding the failures part of risk management and resilience, we may be able to understand and control the system. And this is not only a sensor question, the fact to understand your system, because there may be a point where you didn't put a sensor because you didn't think about it.
Absolutely.
And if it's a black box except the sensors, it's not really resilient. And it is one example of that are modern cars that have a lot of sensors, but that are really harder to maintain and to repair than previous cars, because these are more complex systems.
Absolutely. Right.
And yes, so a question that I can ask to you is that is there some bridge between your analysis and more risk management related resilience analysis?
So I think, there is a bridge. I will talk to you from my point of view. Our understanding is that if we want to assess the resilience, we must clearly identify the mission. So each strategy of resilience is dependent on the system on which we apply it. For example, a strategy working for a water treatment system will not work for vehicular systems, for example. And here the advantage is that we have static systems and we focus on water dynamics in order to quantify the resilience, you know. But I agree with you, if we consider more complex systems in which the human factor interacts with a high density of links, if I can say, there is a higher complexity to consider to assess this resilience. But with risk management, we do not explore this aspect, actually. We focus on the intrinsic properties of the systems, making him resilient, you know. But I'm pretty sure there is topics to explore to make this two bridge that you talk about.
Because what you show the models with the box and the arrow, this really similar to what we can see on the literature on resilience in risk management.
In risk management, yes. Pas de question en ligne.
Last one, which is probably very silly. So I was thinking about the attacker that goes on the cyber layer and just sees the cyber layer. Are there ways to add noise to this cyber layer, like adding nodes that do not anything else but spit out noise and exchange fake data that are not involved in the mission?
If you consider the virtual dimension, yes, they are able to do this. Actually, if we consider the cyber layer, we only think about what an adversary can learn from the system. We do not imagine that he can act on the system in order to disrupt it from the inside view. You know, we assume that his target is to identify critical points. But if we assume this noise that you talk about, yeah, I think he is able to do a lot of things, especially from the network point of view. That is separated from the physical and the layers of the model.
Yeah. What I was saying is when you design the system, you do your mission thing, and then on top of that, you add a subsystem that does nothing but be a perturber for the cyber attacker. So I was wondering if doing this you can.
But we can also do this from the defender point of view with honeypots, for example.
But I'm speaking about the defender point of view.
I thought you talk about the adversary point of view.
No, it's the defender. Like
yes.
You artificially increase the
resilience,
the standard deviation zone by putting nodes that do anything useful.
Yeah.
But I don't know if this increases the attack surface or not. Maybe it does.
We considered these aspects, but we are not able actually to quantify how it updates the resilience, how it impacts it. But these are countermeasures very useful, yeah.
And another question that I have is that from architecture 1 to architecture 2, you can go to another architecture in an automatic way, or this is something that you need to do manually?
What do you mean going to an automatic way?
Like I take the architecture 1, I go to the 2 adding stuff, but can I add it in an automated way without having a human deciding that I need to put this?
This is a POC that we want to develop at SystemX. We want to have an application on which we can play, if I can say, with the resilience potential. What happens if I add this components, and analyzing what is the best resilience score?
Okay.
But actually, it is handmade, if I can say it.
Yeah. Okay, thanks a lot.
Thanks a lot.
So I don't think
there is no questions online.
Questions online. I think we're all good in the room. So thanks again.
Thanks again.